Ooh, recording. If we want to flip 3 fair coins, or we flip 1 coin 3 times, either way we do it. How many possible outcomes are there? That's the first thing, I guess, huh?
Isn't it 9?
7.
It's 8, isn't it?
It's like right in between the first two y'all said. It's like 9, 7, 8. How do you, what's like a good way to do this? Is it gonna be what, heads or tails? That's the first time. Do y'all remember how to do this thing? This is probably the best way to exhaust all your possibilities. There's all of them out there. This is like first flip. So my first flip, I'm going to get either a heads or tails. On the second flip, I'm going to get what?
It's 3 coins, sir.
Yeah. First,
But
second,
for the-
third.
So you first flip, you get head, tails, tails.
You
Or
get heads or tails.
heads.
So on the first flip, you're either getting heads or tails on the first one, right? On the second
Okay.
coin, you're going to get what?
Heads or tails?
Heads or tails.
Okay.
Right. And each time I'm splitting this how many times?
Twice.
Twice, basically. And then you follow your branches. So how many options should I have? Count them all out.
8.
There should definitely be 8. This also goes to the 2 times 2 times 2 sort of thing, the accounting principle. You have 2 options here, 2 options here, and 2 options here. We're multiplying the total number of options for 8 options. Follow your branches. The first thing says heads, 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 tails. Heads, tails, heads, I think is the next one. Heads, tails is the next one. No, it should be 8 anyway, right? So I don't know if it's obvious. TTH. TT. Sorry, I didn't like put them. But those are being divided, I guess, right? I got heads, 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 tails, tails, heads, tails, heads, heads, tails, tails, heads, tails, heads. I think I just said Teds and Hills. Okay. And the last one is all tails, no Sonic, right? So what is the probability of getting heads, tails, tails when you flip 3 coins? How many out of how many? It's going to be a fraction. That's probably the question.
1 out of 8?
1 out of
It's
8.
going to be one of the options out of the 8 options. Where did I throw my calculator? Back. It's hiding underneath a piece of paper. There we go. Okay. 1 out of 8 is what? 0.125? That's it. I don't know why I need a calculator for that. I should know that one. Half of a quarter. What is the probability of getting 1 head when flipping 3 coins? So this, I'm going to do it out of the 8 options still.
7 out of 8.
1 head?
Is it just 1 head or at least 1 head? Oh,
Just getting 1.
It's getting 1 head.
okay.
3?
That'd be Jesus.
3 out of 8?
3 out of 8.
We got to count them, right? This one,
Yeah.
this one. That's 2 heads, 2 heads, 2 heads, all tails, all heads. So I believe it's the 3 out of 8. Which is what point? Oh man. Or 0 point, yeah, 375. And so this is really getting at the concept of I have a outcome versus an event, right? I'm looking at like a single outcome of heads, tails, tails. Here I'm looking at an event of one head. I could have said at least one. That would have given me 7 out of the 8. Seem fair, hopefully.
Yeah.
If y'all can remember how to do these things, right? These things will really help you with getting all your outcomes out there. I'm doing the first one. It's either going to be heads or tails. I'm branching out from this to do my second one. This one can be heads or tails. So this is now giving me 4 options, right? If I do 3, it's going to give me 8. If I do 4, it's going to give me 16 options. So I'm probably not going to make it any more than 4 on there, right? You start getting really, really large if I want you to list all the outcomes. It might be a probability because we can crunch that with some of the theory stuff, right? You flip a coin and you believe it's fair for 100 times and it lands on heads 45 of the times. Compare the relative frequency of getting heads to the theoretical probability of getting heads. So what's my relative frequency here?
It's gonna be 45 over 100.
Yeah, 45 out of 100 or 0.45. Relative freak. And what is the probability?
One out of 2.
Okay, a half or 0.5, right?
Yeah.
Okay. Okay. And then, what is the relative frequencies of tails? So they don't give us this, but there are a few different ways to get it.
Subtract 45 from 100.
Yeah, you can subtract 45 from 100. So one way you can think is there will be 55 tails out of 100, right? Or 0.55.
Or you could do the P not A, 1 minus P, the,
Well, yeah, exactly. The 1 minus the 0.45 will also give you the 0.55. So either way. And this theoretical probability of, I don't want to give it away too fast, but it's still a half, right? Heads is a half, tails is a half. 50-50 probability. Is there reason to suspect the coin is unfair?
No,
So
No. Why? Like explain.
because each flip is independent of the previous one. It's all chance.
Yeah, I think they're wanting like to explain maybe like why is this 0.45 versus 0.50? Like the moral of the story here is that like your relative frequency, right, is not going to be exactly your probability.
I thought it was because the amount of times that you do it.
Yeah, that's also a factor, right? We're only doing it 100 times, but these two things are probably never going to be exactly the same, right? They might be by coincidence, right? But almost most of the time, these things are never going to equal each other. Like when we do things in reality, like when we flip a coin or we roll a dice, it's not going to come up 50-50 probability exactly, right? If I flip a coin right now, things don't work precisely, right? Like this. But over the long run, this thing should start approaching this, right? So the law of large numbers actually does kind of come in here. They just don't say it yet in this section. This was like one of those problems from 4A. They're kind of hinting at the law of large numbers before we get to it a little bit. But if you wanted to say like relative frequency is not going to be exactly the theoretical, right? This is an ideally fair coin. And in reality, are coins really fair? Not exactly, right? They might have a little bias to them. And even if they are fair, right, this still can come up. Even if it is completely fair. Even if it's equally weighted and has equally probable chance of getting flipped. There's some really kind of weird stuff. With asking, is the coin flip really random, right? But I think it's getting into maybe something a little deeper than what we get into this class, though. If we flip a coin, is it really random? We assume it is for this, right? Like theoretically, we have to assume it is. But in reality, is it really ever random when you flip a coin? Because the flip of a coin is just a bunch of physics. Like you could actually calculate exerting what, like, you know, what force is being exerted on that coin, exactly how it's going to flip. Like if you know
Yeah.
all the factors in that thing, it is just a
Yeah.
physics experiment. If you calculate all the vectors, you know exactly where that coin's going to flip.
See, I was just thinking about that because I was just in my head right now. You were talking and you just hit it because I was like, when you said about the times, right, and that it wasn't enough times to hit it, and then you start talking about the factor. I was like, well, if you add that, then you have to factor in the wind current and the hand and the table that it hits when it turns on the table, if you flip it on the table. And so I was like, okay. And then when you just said that, okay, I understand.
Yeah, but I mean, there's this question of like, is anything really random, or is random just sort of like this word that we use to like mean our ignorance of the forces at play, right? Sort of like that. And I'm not sure I have an answer for that, to be honest. I've thought about that a lot. But sometimes we assume things are random, right? And we do it because it works out and because we can use this, and this is applicable on a lot of stuff. And it helps explain the reality around us, right? The relative frequency is not ever going to be exactly your theoretical probability. The way things play out may not be exactly the way things figure out theoretically, right? So reality differs from, reality can differ from theory a bit, right? That's basically what they're getting at here. The reality of the situation can differ from what we're sort of figuring out here. And also it's kind of hinting at the law of large numbers. The larger you get, the more your relative frequency should get closer to your theoretical probability. But that's not even necessarily guaranteed, right? It should typically. What is the probability of getting 2 when you roll a fair-sided die? So this one I hope is not super hard. How many times how many events or outcomes does a 2 represent?
1,
It
One.
represents 1 outcome out of how many outcomes?
6.
6.
6 possible outcomes. So this one, I'm just trying to kind of set you up here, right? What is the probability of rolling a 2 or 4 when rolling a fair-sided dice twice?
So that is,
2
0.
or 4, 2 and 4.
so that's 2.
You're gonna roll it twice.
So that's 2. So that's a 1. That's 2, and you're gonna roll it twice. That's so that's 2, 4 over 12. Is that 4 over 12?
So this, I'm trying to get at this word "and," right? If I roll a dice twice, and the first roll I get a 2, and the second roll I get a 4, is what this is saying.
Oh,
What is
2
the
and a 4 at
probability?
the same time.
Would it be a
Yeah.
1?
You could roll 2 dice at the same time, and this would be the same problem, right? You're either going to roll one dice twice, or you're going to roll 2 at the same time. What is the probability I will get a 2? We've already
1
said
over
One.
6.
And what's the probability I will get a 4?
1 over 6.
Okay, so how do I find the probability of getting both of those?
multiply.
I multiply these. And if you want to do your tree with this, I guess you could 1, 2, 3, 4, 5, 6. And then you'd have to have what, 6 different things coming off of each one of these. 1, 2, 3, 4, 5, 6. I didn't leave myself enough room, but there's 6 coming off of each one of these numbers, right? I'm going to have 6 by 6, where I'm going to have 36 different options. And rolling a 2 and then rolling a 4, that's how many options out of all of them. 1 times 1 is?
136.
It's 36.
Yep. Okay. What is the probability of getting a sum of 5 when you roll 2 fair-sided die? And I'll give you a hint, like make the table for this. So like die 1 is like 1, 2, 3, 4, 5, and 6, right? I'm gonna go 1, 2, 3, 4, 5, and 6.
Jesus.
Yes.
I didn't know that that's what it required. Oh my God. Okay.
So this is like die 1 over here, right? And this is like die 2.
Yeah, die one.
However you want to
die
do it,
two.
right? You can swap them up. It's not gonna matter too much.
You know,
But these are sort of like
we
what
haven't
goes
done
on the
no reading.
outside. On the inside here, let me do it maybe with a different color. I want to do the sum on the inside. So 1 plus 1 is going to give me 2. Here, 2 plus 1 is going to be 3, 4, 5, 6, 7. I can go 3, 4, 5, 6, 7, maybe this way as well. Three, 4, 5, 6, 7, 8. 4, 5, 6, 7, 8, 9. So this is something you should be able to do, hopefully. 6, 7, 8, 9. 10. This one should be 6 and 6, should be 12, should be the last thing I do, right?
Okay.
11, 10, 9, 8, 7, 6, 7, 8, 9, 10. Okay. How many different options do I have here? I'm looking at all these different possible outcomes. How many different outcomes are there?
36.
There are 36. There are 6 by 6 little entries in this table. All right, and so they want to know what is the sum of what number 5? So if we make this table, you might notice 5s are all where? Kind of in the same place, probably. Hopefully. Is this like a word search, but with numbers or something? Circle your 5s. You notice they're all on a diagonal. Things that add together to the same number are going to be in a diagonal on this table. And so what's the probability of getting a sum of 5 if you roll your die?
This one.
4 out of 36.
4 out of 36 is absolutely right. If you give me 4 out of 36, that's beautiful. I think we can reduce this, divide both by 4 into 1/9, right? How long do Power Wheels batteries last?
A while, I think.
Yeah, I remember they always used to die when I was a little kid. I don't know. They probably got better batteries now though too. Battery technology's come a little bit of a way. Okay.
All right.
So I'm making use of a standard deck of playing cards.
Mm.
Ain't nothing to see here. Just a normal normal pack of playing cards. You can observe them yourself right here. Look at that. What is the probability of drawing a 10?
4 times.
That's 4 times out of how many?
Out of 52.
Out of 52.
Hey, you know, you right in my arena right now, Professor. That's it.
What is that? 1 out of that's same as 1 out of 13, right? I don't know why I did that.
So this is 8 out of 52. Oh, sorry.
A 2 or a 10? What's the probability of drawing a 2? And this is trying to get at the or thing, right? Drawing a 2 would be 4 out of 52. Drawing a 10 would be 4 out of 52. If I
Yes,
want to put them
8
together,
out of 52.
if I want to put them together with an or, I'm talking about a total of what? 8 out of 52. I think that's 2 out of 13 is another way to look at it. You're talking about two of the numbers out of a suit. All right, so they're going to get a little more challenging, I think. A 2 or a diamond? The probability of getting a 2 is 4 out of 52. The probability of getting a diamond, you could say 1 out of 4, but I would go with the
Oh, a diamond? I thought that diamond, okay, a diamond. So we got 12. I mean, sorry, 13.
there are 13 diamonds in here.
It's 2 out of 13. I mean, 1 out of 13. Sorry.
You could say 1 out of 4 if you wanted to do that, but I don't think it would benefit us to reduce it here. Because if we do this, you'd be oh so close. You're going to forget one thing if you do this.
You have to subtract 1 out of 52 for the 2 of diamonds.
Exactly. So this is if they're overlapping, right? So we did not have that problem on this or. So this was like 2 and 10. So if I wanted to circle 2 and I wanted to circle 10, you're going to notice those circles do not overlap, right? They are completely separate from each other. They are 2 different numbers. They're not going to overlap. But now when I go to what? Diamonds and 2s. If I want to circle that, I'm circling this set right here. I'm circling this set right here.
So it's 4. 13.
So there are 4 2s. There are 13 diamonds, but there's one card that I counted twice, which is the 2 of diamonds.
2 of diamonds. Ah.
So this is 17 minus 1 gives me what? 16 out of 52. Oh, what is that? 16 out of 52 reduces to
11 out of 26. Wait, just kidding. 4 out of 13.
17 over 52. And then it's 17 over 52. And then you minus 1 on 52, which makes it 16 over 52. That's right.
Yeah, we're going 4 plus 13, and we're subtracting 1 from it.
And then a divide.
And we have it all, they're all over 52. If you have them over the common denominator, you keep the common denominator and just do the operation with the numerator.
Okay, I see it. Okay.
Yep. Same thing here, right? If we get a common denominator, which is part of the reason why I'm not reducing my fractions. Don't reduce your fractions and they're easier to add, right?
Okay.
If you keep them out of 52 and everything's out of 52, it's a lot easier to calculate stuff. What is the probability of drawing a face card or a club? So now this is something, I don't think we've had this one before, but it is a good question. A face card. So how many face cards are there? 3
30.
by 4?
I mean, excuse me, 40.
What? 3 by 4.
I mean, I'm sorry. I'm tripping face cards. I had to read these questions right. Jesus. 12. 12 is
All right. So we count the face card. There are 12 face cards out of 52. There are how many clubs? There are 13 clubs out of 52.
12.
And then if we do this, we have to, is there an overlap here?
Yes.
Yeah.
There
3
are
out of
clubs that are
52.
face cards. There are, I think someone said it,
By 3.
3 cards that are face cards that are clubs.
3.
Yep. Then we're talking about what? The jack, the queen, and the king of clubs, right? If we circle our clubs, I don't want to put too many circles. Maybe a different color.
Professor
circle.
Steve,
Yeah, what's up?
I have a question regarding the test.
Okay.
Is the same thing gonna be on the test, like the clubs and stuff? Because I have no idea what clubs and stuff are like that.
Yeah, I mean, that should be on your test. It is something that's applicable.
Are you gonna print out this little chart though of the cards, I think?
Yeah, I will print out this chart of cards. So I think, would that help?
I mean, I really wouldn't tell you, like, if you would ask me what's an ace, I don't know what an ace is or a club. So I think that I would have a little bit of a problem there.
Okay. I'm trying to think of what I can do that will I get around that. Because this is a club, this is a diamond. So it is divided into 4 different suits, right?
Maybe you could do a little key on the test too that says like, this is what a club is, this is what an ace is, and these are what face cards are.
Yeah, I could do this. If I ask you for a suit, I'll put the suit on here like that. Would that make it more fair?
Yes, thank you.
I could put the suit on there because I didn't even think about about putting the suit. But if I put them like this, I'm trying to think of how I'll do it. I mean, a number is a number. I think you should be able to see what a 10 is, right? I'm trying to think of how to adjust this and suit it. Okay. Yeah, that's something to consider. Let me think. I'm trying to see. Yeah, face card's kind of a weird thing. So I might probably not something I'm not going to test, but I don't want to say that out loud. So if we look at this is 12 and 13 gives me what, 25, and then have to minus 3.
25, 52. Then 3.
52. Yeah, right. Should be 22, right?
22.
12 plus 13 minus 3. 22. 22 out of 52 is going to give me 11 out of 26. Okay.
All right. Okay, let's go.
We are drawing 5 cards at random without replacing. What is the probability that you will draw 5 clubs in a row?
5 clubs in a row.
I would think about these sort of sequence. I'm going to do card 1, card 2, card 3, card 4, and card 5. And when I say I want to do this 5 times in a row, is this like, what kind of statement is this like? I want to get this
Like
card.
you're taken away. Like once you pull a card, you gotta take.
Yeah, I want to get this card. And is it and or?
And
It is and. I want to get this card, and I want to get this card, and I want to get this card, and I want to get this card. Does it make sense why I'm saying this is and? If I'm getting this card and the next card and the next card, I'm being
Yes.
very specific. I'm getting 5 clubs in a row. Okay. So what is the probability of getting the first club?
13 out of 52.
52. Oh, there you go.
That's the 13 out of 52.
Is this one of those questions where you keep on lowering the amount of cards that you have in the deck? Like the next time would be whatever the top number is over 51?
That's exactly what you do. And so each time we're taking one from the deck. So each time the number that we're drawing from should go down 1 by 1. And if someone deals you poker like this, you pull out that revolver issue to
I'm
you.
gonna have a fit.
Because you usually go around in the table when you draw poker. This is not how you draw.
No, you keep them cards in that deck.
Yeah. But this is the way we're doing it. They're just going to let you draw 5 in a row. We're not replacing them. This goes 52. This is 51. So now this is
12.
12. We're going down each time because we are drawing a club. So this is like the clubs to the total is what I'm thinking here, right? There are 13 clubs. There are 12 clubs. There are 11. There are 10. There are 9.
9.
And I probably didn't leave you enough room to finish this thing off.
So now, with those numbers, do we add them together?
This is all an and statement. So what do I do when I have an and statement?
Add.
Ors or add?
Oh, damn it.
What do I do when I have an and?
Multiply?
It is
Multiply.
And like one of the indicators that might help you, like if I add fractions, they're going to get larger, right? If I think about this, the probability of getting like very specific cards, getting 2 cards of the same versus getting 3 cards of the same, it should be going down each time, right? And so if we multiply by fractions, we get smaller numbers. So looking at whether your fraction is going up or down might also kind of help. This is going to get a smaller result. So in the bottom, I'm doing what 52 times 51 times 50 times 49 times 48.
2.
So I'm going to get a ridiculously, obnoxiously large number. 31,187, 5, 200. So this is the total possible ways that you could draw 5 cards, right? At random, I think is what that's giving you. Total different number of outcomes, like 300,000, something like that. 300 million, sorry. Looking at the wrong spot. And then on top, I have what? 13 times 12, 13 times 12 times 11 times 10 times 9. 154440. Probably not going to be a very large number. Which, if you think about getting 5 of the same suit in a row, you're probably not going to get a very large number. It should have 3 zeros in front of here and a 495, somewhere in that ballpark.
$49, 48. Jesus, is that 305?
Mhm.
Okay, I got 305,760. Jesus. How did I hit?
Did
You
I do
got
that?
311?
Doing 52 times 51 times
Let me
50.
do this again.
Is that what you're doing?
Yeah. Oh, I missed 51. Darn it.
52, 51, 50, 49, and 48.
Okay, hold on.
All right, so the next problem is a bit of a silly problem. All right, can I get this all on there at once? Probably not. I'll throw it up there for people still working on that little part. But I'm gonna go ahead and read this. Imagine you draw 5 cards at random without replacing them. What is the probability that you will draw 5 aces in a row?
You can't. There's only 4 aces.
Okay.
Yeah.
That's the first thing you should acknowledge. And so what would the probability of that be? It's a really kind of silly thing, but we could always say the probability is
0.
0. Another way, if you really wanted to think about it, you could maybe say, oh, the first ace is 4 out of 52. The second ace is like 3 out of 51. If you wanted to be really silly and do extra work that you didn't need to do, you might notice that you get down to 0 aces on the last ace. There's no way you're going to draw a 5th ace is another way of saying this, right? So if you really want to do some extra work, you could do some extra work. But if you know you only have 4 aces in the deck, you know there's no chance in heck of that happening. You know the probability is 0, right? And it might be a bit of a silly problem, but I'm trying to get at the fact that 0 is a possibility, right?
0. Oh my.
0 is something. What is it? It's nothing.
It's nothing.
That's why people just.
Why can't we just say the probability of drawing drawing 5 aces is 0?
Okay, areas is it going to happen?
Yeah, that it's not gonna happen.
It's not going to happen. How do we say it's not going to happen with probabilities? We say there's a 0% chance that's happening.
Okay.
Where we at? I feel like my tests are getting a little bit shorter. Test 4 was just like a really long, kind of long. Had a lot of stuff to plug in and stuff. Not really like. I don't feel like concept wise it was as deep as this is, but like work wise they make you do some elbow grease writing all that stuff down. I don't know. It's like a lot of ink and paper for those. Imagine you are rolling a fair die and betting on whether it will land on an odd or even number. You roll it and it lands on an even number 13 times in a row.
13.
Your friend points out that you're overdue for an odd number any row now. Roll now. Is this correct? What should you bet on? What is the probability that it will land on an odd on the next row? What is the probability that it will land on an even in the next row? So getting this right away, how many odds and how many evens are on my dice?
3.
Yeah, there's 3 of each, right? There's 3 odds and there's 3 evens. So a dice is kind of evenly split down the middle if we talk about odds and evens.
Yeah, craps is my favorite game too. Along with poker. Yeah, 3 odds and 3 evens.
Yep. There's not too many casinos in Texas from what I looked at.
Yeah, there is.
They don't really allow gambling so much. But I think certainly reservations and stuff might have some permits. There's like some really odd places, but it's like I feel like they're like all ritzy high roller kind of in stuff. And you
Well,
gotta-
yeah, all mine was in casinos.
you probably got to have money to get into them in the first place.
Yes, you do.
But there's a lot of like workarounds, and you always hear people getting busted for stuff like that in Texas too. I know I've walked in a few like bodegas and little like gas stations, and they have like the one on
Yeah.
bandits in there that you can play for credit in the gas
You're
station.
not supposed to
Like,
do that.
okay, yeah, not really my thing, but man, there's obviously some people that it's an addiction for some, I think.
Yeah.
Let's say that. So, what's the best bet? Is there a best bet? What is the best bet? How's the best bet go on this?
The 13 times in a row.
Mm-hmm.
So the 13 times of them receiving
Nothing but even? Is that what it was? Yeah, even.
even.
We just roll it 13. Every time it comes up an even number, your friend's saying, well, you're overdue for an odd. Should you place a bet on odd?
Yeah.
What was the probability it will land on odd?
Probably get it.
50.
Probability to land on odd is still 3 out of 6 or 50 for that.
Yeah.
That 14th roll, the probability to land on odd is 50, and the probability it will land on even is what?
50.
50.
Exactly the same thing. So for that 14th roll, what is the probability of odd and even? It's still
50.
a 50-50 shot. So is there a best bet to place on this thing?
Well, no, I mean it's not, because you don't know if you're gonna win or not. No, but I would take the chance.
No, it's still a 50-50 shot, though, right?
Yeah, because it's a 50-50. I could win. I guess not like a 60-40 or 70-30. I still might win.
Out here is that they're both equally probable, right? There is not a better bet, so to speak. Like it's not better to bet on odds than it is even. Even though we get this like run of evens, there's nothing that guarantees that next roll is going to be an odd, right? There's nothing in the short term that guarantees that. And so this is that trying to get at that law of large numbers thing, right? In the short term, we still have 50-50 odds on this thing. There is not one thing that's better than the other. We get 13 times in a row, runs happen. Short-term runs absolutely happen. Sometimes you get the runs. Something you gotta deal with.
Sometimes you get the runs.
Happens.
Yes, it does.
For number 6, was there a print or typing error or something like that?
Oh shoot. Yeah, I did not finish that problem, did I? That did not get copied and pasted. Okay. Let's do something then. Let's say 1 in 125 of doing $1,000 payout. There is a 1 in.
Oh, that's part of the question.
$10,000 payout.
Was that 12.5 or 125?
1 in 125 of $1,000 payout and 1 in 571 of a $10,000 payout. So I could do more and more. I think this will get at the point, probably good enough. I probably went to like copy and paste there something, and then you get copy and pasted. And I probably really should have more, but this will get at it good enough, I think.
All right.
And we are trying to figure this out from the insurance company point of view.
Expect to make it. See this.
So I want to find how much should they expect to make. Keyword here is probably this word. I'm looking for what here? Do you remember this thing? What it's called?
Expected value.
The expected value of this game. The game called insurance, right? So if I'm the insurance company, first thing I want to talk about is this 125. This is my value. And is it positive or negative? Am I getting that or am I paying it?
Positive.
It is positive because I'm getting it. And it might seem a little silly, but what's the probability that I will get $112 out of this person?
1.
1. And then I want to talk about a payout of $1,000.
Should be negative 1,000.
Should be a negative 1,000. So this is my value of, you could say like plus or minus 1,000 if you really want to be crazy, but it's a negative 1,000. And the probability on this is what?
1 over 125.
1 over 125. And we're doing value probability to find the thing called the expected value. Sometimes they call it E of X or something like that. And the last one says what? I'm going to pay out, I believe, what, $10,000, and I'm going to pay that out 1 in 571. Does this even come out reasonable since I just threw in numbers? I have no idea. $1,000 divided by 125 is going to give me -8. So this is going to give me 112. This is going to give me something like -8. And what, -1751. So it probably works out fairly reasonable, I think. It's probably a little inflated from what happens in reality, but it'll work for an example. We can get the value of what, 86.49.
Okay, so did I do how did I do this? Did I do 10,000 times 571?
10,000 divided by
I'm
571.
sorry.
That's what it's going to end up being. And so we're multiplying these things. You're multiplying 10,000 by 1 over 571. Another way to look at that is if you have a whole number, you can always kind of sort of put them over the number 1. The 10,000 is going to end up in the top. The 571 would end up in the bottom, or we'd be dividing those two things.
Okay. Is that the same with the 1,000 as well?
Yeah, you can put this over 1 as well. It's going to end up in the top, and this is going to end up in the bottom, right? And it's going to end up being division.
Okay.
Multiply. It's kind of like multiplying by a half would be the same thing as dividing by 2.
Okay.
If you multiply by the reciprocal, or it's like dividing by the reciprocal, right?
That's 112. And this is 8.
Okay. So this is, we're making 86.49, and that's for every what?
And that's for every policy.
That's for every policy they sell. In honesty, this is really probably a high number. They're probably going to make like $5 a policy or something. But if they sell 1,000 policies, how much will they make? So we're moving this how many decimal places? In which direction?
3?
3.
3 to the right. To the right. And so we're going to have to end up adding a 0. So I believe it should be what, 86,490.
So 1, 2, 1, 2, 86,000. Yeah. That's right. 86,000.
And just so we have it here,
That's crazy.
times 1,000 is going to give you that, right? Any questions about this? I know I messed up the problem by not putting it there a little bit, but I think this should be manageable, right? I'll fix this. I ain't got no proofreaders. One person proofreader is what I got.
Oh,
And that's me. It does. Oh man, it's like, and like the power of suggestions really influential when you're doing these things too. Like I will look at someone doing a problem, doing it completely wrong, and I'll just like nod my head up and down, like, yeah, that seems correct. Like it is so hard to like catch where people go wrong sometimes. Okay. We'll place a dollar bet on a single number on a roulette wheel, which has a 35-to-1 payout. This means you will win $35 in addition to the dollar you originally bet. Betting on a single number has a 1 in 38 chance of winning. How much should you expect to win or lose each turn? And this is one of those things, there are basically 2 different ways you can do this, I think.
1 over, is it 1 over 35?
Okay, so the first thing is we're placing a dollar bet. And so if we're placing a dollar bet, are we gaining or losing a dollar?
Oh, we're adding a dollar.
Losing?
Losing.
We're gonna lose that dollar. And what is the probability we will lose that dollar if we play this game?
1.
1 in 38. Oh, 1.
We're gonna lose a dollar if we play the game. So we've accounted for this dollar that we've already paid. There is a chance that we can win $35. And if I win $35, I'm also going to get this dollar back. So all in all, I'm going to win how much?
36.
I'm going to win $36. And what is my chance of winning $36?
1 in 38.
38.
1 in 38.
Okay.
And so if we want the expected value, is what they're kind of asking for in this problem. So maybe I kind of jumped a little quick on that. But how much should you expect to win or lose each turn? That is the expected value, right? That is the definition of the expected value. How much should you lose each policy or each turn? On average, how much should you win or lose? That's what the expected value is. If we do this, hopefully I set it up right, -1 plus 36 over 38. What is 36 over 38? Is that like 0.94736? Or some change. All in all, we should be getting something around a negative 0.053, somewhere in there. It's like 526, right? Something like that.
I must be doing this wrong. I keep getting 119. What am I doing?
This is negative and this is positive.
Wait a minute. Oh,
So I think maybe you're doing both the same sign or something.
yeah,
Sounds
that's
like.
what it looks like. Okay, hold on. -1.
So what is this telling me? For each game I'm playing, am I going to win or lose?
Lose.
You're definitely going to lose because you're at a casino. That's what the point of the casino is. And you're going to lose about how much?
5 cents.
Yeah, a little over 5 cents, right? Okay. This is one way to set it up. You want to see the other way? I don't know. If this confuses you, just ignore it. There is another way to set this up where you don't account for the fact that you paid the dollar. If I don't account for the fact that I paid the dollar, I'm going to win $35 1 out of 38 times. And I'm going to lose $1 37 out of 38. And if you do this, I think you get the same number. Does that work right? 35 out of 38. And we're going to subtract what? 37 out of 38? Yeah, it gives you the same number. So you have to do it one way or the other. I'm like really hesitant to show you this because now you're just going to confuse the two ways maybe, but hopefully not. If you account for the dollar that you get taken out, you have to put the dollar back in, right?
36.
And we could also think about maybe we're going to win $0 37 out of the 38 times here. If we don't get it, I don't know if that helps. But if you account for the dollar getting taken out, you have to account for getting your dollar back, is the moral of the story here. And if we don't account for the dollar getting taken out, you have to account for losing it 37 out of the 38 times. I would personally probably set things up like this. I think this is probably the easier approach. This is the approach that the book,
Oh, I got it.
the book went with.
Okay, so that's what I messed up. So I'm supposed to be 1 divided by 38 times 36.
Yep.
That's what it is. Okay.
Or you could do 36 divided by 38 is the same thing. Okay, so this is how much you win or lose each turn. What if you play 35 turns?
Times 36.
Would you just multiply that by 35 here then?
You multiply that number you just got by 35. And so I didn't round this. I don't know if it's going to come up minus 0.053. Ooh, missing a 0 on there. Let me see for how close this comes up. Yeah, if you don't round it, you get like minus 1.84. If you do round it, it's around like 1.86. So as long as you're getting within a few pennies of it is what I'm really concerned with. I'm not really concerned with 2 cents, right? And if you round it to 0.526, it gets even closer, right? 1.84. Okay. Questions about this thing? This is negative money per turn. If we do 35 turns, we should be expecting to lose around $1.84, $1.85.
So I don't want to be the that person. But is there a way, since there's going to be such a long break in between our review and our tests, that you could maybe post like just a review sheet with practice questions that those who are interested could just do in the meantime? Like not for a grade or anything, just like,
Just like a refresher type thing.
yeah.
Yeah, like I'm trying to think. Because I got to do this and I got to make a test that is like similar to this.
Right.
Yeah, and yeah, I could maybe like doctor up this quiz a little bit maybe. But I'm trying to think of how we're going to do that, because it's going to be like Tuesday, you're already taking the test.
No, I want to just.
Well, it wouldn't be like a review for us to do in class. I think just something we could do like over the weekend to kind of keep this fresh.
Yeah, I could do that with a few problems. Just I can tweak this around a little bit with the numbers maybe. Would that be
Okay.
better?
Yeah.
And then we could probably do something from there. And I could probably post up a key then too.
That would be helpful if you could.
Yeah,
At least for
there
me.
is a break and I don't want y'all give you a little something. Okay. Yeah, I could probably do something like that.
Thank you.
Okay. Wow, this is the final problem. We're just gonna get.
Oh my God, this is the one I forgot.
I put a big black bar here so it would block out the numbers that they give you, because I'm gonna make you figure those out. And then when I was when printing this out, I was like, oh, that's doing wonders for my ink right there. I probably should have made that the white box, but you live and you learn. Design.
1998.
There's a lot of crazy things I didn't realize with color palettes that exist. So I started doing programming and they start talking about like tertiary colors and stuff. There are definitely certain colors and color schemes that like you want to pick for certain things.
So is this a meridian question?
A what? Meridian?
An average meridian question? Because that's a lot of numbers there.
Are you talking about the median? Is that what you're talking about?
Yeah, what did I say, meridian?
I was like, what-
Yeah.
this is just like, this is coming from that last chapter that we had for E. They gave a lot of vital statistics, and then they asked
my
you
God.
to convert. They asked you to convert like deaths per miles traveled or deaths per 100 million miles traveled.
Yeah.
Remember that? And they ask you to find death rate per person or per 100,000 people. There is a reason why they're converting these things too, and we'll talk about that maybe. Compare the death rate per person in 1998 and 2018. So 1998, there are 41,501 out of how many total? 276 million, 0.1 million. So 276 million, 100,000, and a bunch of zeros.
Okay.
Wait, for 1998?
Did I do that right?
Okay, you said 41,501. I got that part.
It's 2,625,367.
Okay, so where do you guys get that part? Oh,
Yeah,
270.
we're doing death rate per person.
So the population 98 was 276, and the population 2018 was 320.
The next one we're doing per mile, so that's what you're looking at.
Oh, okay. Thank you. Sorry.
Okay, Lisa, you
I don't know what it is. I've just been having trouble picking out words today. I've done that on like 3 problems. I'm so sorry.
So
Nah, you're doing good.
so this we're doing it twice, right, Professor? One for 1 for 1998 and one for 2018, correct?
Yep.
Okay, I got it.
And so this is giving me somewhere in the ballpark of 0 point, and I should get 3 zeros and then a 1503, somewhere in that ballpark, 1503. And this is what, in deaths per person? He didn't even kill a whole person. How do we do deaths per 100,000 people?
Times that number by 100,000.
If we multiply this number by 100,000 is a good way to do it. If you divide this number by 100,000, you could also get it, right? So we're either dividing the denominator by 100,000 or we're multiplying this thing by 100,000. But anyway, that's like saying 3, 4, 5 places. And if we're multiplying, it should get larger by 5 spaces. So if we go 1, 2, 3, 4, 5, I think we're getting about 15.03 deaths per 100,000 people. And I definitely didn't leave you enough room to work that all out down there, but you got the back of a paper on there too somewhere, right? Okay. And then we're going to do the same thing for 2018. Is that the other one we're doing, 2018?
Yes. 3.
In 2018, I'm looking at that table. It's giving me 36,560. And my 2018 population was 327, 200,000. And so what are you going to say? Larger or smaller? What should you
It
probably?
went 0.000111736. That's what I got. So I don't know.
I'm getting 1503 on that one.
No, not. Oh, you guys are doing.
Oh, you're doing this next one. Is that what you're saying?
I was doing 2018. I'm sorry.
I thought you were asking about the other one. Never mind. Sorry. Yeah, that's it. 0 point, and we get 3 zeros again. We get 111,736.
736. Yeah. So we
Somewhere in that
divide
ballpark.
that number by 100,000, correct?
This is your deaths per person. So maybe write EH in deaths per person. We divide the number of deaths by the total number of people, we get deaths per person.
Okay.
And then you say divide or multiply?
Do you divide by 100,000 or multiply?
If you divide this thing by 100,000, you would put this into 100,000 people, right?
No, the number, the total
But this thing, we want to do what?
divided by 100,000.
Not divide.
Multiply it.
It'd be multiply.
Oh,
And if we multiply by 100,000, that's like moving it 5 spaces. To move that decimal 5 spaces, I think we should get something a little bit smaller, point like 17, something like that. Deaths per 100,000 people. And I know it might seem kind of weird, but does it like, and I don't know if I talked about this explicitly when we went through that section, but like, does it make sense why they do deaths per 100,000 people versus doing deaths per person?
yeah, it's a census thing. I think.
Like, why? Yeah, but why would they do it? What's the reasoning behind doing this? What are they doing out there? Jesus.
I guess for taxes or
Compare it to like different areas.
Okay, so if you had to compare two numbers, which one is more descriptive? This tiny incy-wincy decimal that says this many deaths per person, or like saying 15 deaths per 100,000 people? Like, this to me makes a little more sense because we're doing whole numbers here. And usually when you do like units and stuff, you want your units to be in whole numbers. I don't want to be talking about fractions of feet, right? I want to be like 1/8 of feet. I want to be like 3 inches, right? If I say something like that, it's like, why do I want to do fractional feet or fractional miles? Why put it into a smaller unit? That's what they're doing. They're putting it into quote unquote like smaller units, so we get a larger number. And this makes more sense to me context wise. What the heck are you saying with this thing, right? I have 0.0011736 deaths per what? That's not even a whole death there. Like, what are you talking about? At least make it interesting. Start talking about people dying, right?
yeah,
Talk about a whole person dying.
not a half a person.
We're all a little bit dead, right?
Buddy.
I want to talk about whole deaths here. So
Okay.
it just makes a little bit more sense to put it in something that is whole units, basically, than to talk about fractional deaths or something silly, right?
Compare the death rate per 100.
And you can look at like populations of people, right? You can look at cities and know how many 100,000 people are in a city, right? Austin's got what, about 9 times this? I think we're close to 1 million, aren't we? Or did we go over 1 million? Do y'all know? Travis County?
Yes.
I don't know. Travis County pop.
I know it's up. I don't know how much.
$1.274 million people in Travis County.
Wow.
So 10 times that is what you would do, right? It's like, oh, I got about 10 times that in Travis County. It's a lot easier than trying to figure out this, right? How many deaths in Travis County? You'd have to multiply this by 1 million or something. That's kind of annoying. I don't know. It's a little bit easier to work with in a lot of things, right? Compare the death rate per 100 million miles driven in 98 and 2018. So this improved by about what, like 4 deaths or something? Maybe a little bit less. We went from about 15 to about 11, right? Per 100,000 people. How does it, we want to compare it to the miles we drive now?
Oh God.
Yes.
That's
Oh man.
600.
I was fortunate enough to have someone that had like a doctorate in math whenever I was in high school. He like taught the pre-cal class, but he would always respond anytime he'd say, "Oh my God." He would just like do that deep booming voice and like, so
Mm.
I'm totally ripping it off from my old high school teacher.
Okay.
Death is 41,501.
Oh, so we gonna do deaths over the miles. Okay,
Death over miles. Now the
I
miles
was doing the miles traveled on the millions. Okay, well, never mind.
we want to know in deaths per mile. 5367. And there's something on the table that they say these are in millions.
Million.
So I need to add
Jeez, I am.
Okay.
how many zeros am I adding to get to millions? I think it should be 6, right? 3 would get you to thousands. 3 more would get you to millions. This would be deaths per mile. You could do it this way. The other way, if this isn't millions and you want it in 100 millions, how would you make this into 100 millions?
Is it so? Okay, how does this? How did you write the if it's 100 million, how do you write it?
I'm not writing it in 100 millions. I'm writing it in deaths per miles right now. And so if I want to convert this to 100 million, I'm accounting for 100 million out of this thing, right? And 100 million is another way of saying 8 spots. So is this going to get larger or smaller by 8 spots?
Larger.
Yeah.
Look larger.
If you want to talk about it as being 100 millions,
It'd be smaller.
it would be smaller by 8 spots. Where's my other pen? So I'm going
Jesus, how did you figure that?
7, 8. So another way you can think about this is I got 2, 6, 2, 5, 3. I put my comma in the wrong spot, huh? 0.67. Sorry, my comma should be there, not here. And this is in 100 million miles, right? So it should be 26,253.67. The other way to look at this is that these are in millions of miles. If I want to make them in 100 millions of miles, what am I going to divide this thing by?
So
Going from millions to 100 millions?
by 100?
Divide these by 100, you will get the same thing. I divide it by 100, I move these 2 decimal spots.
Oh no.
Okay. But if I do 41K out of what, 26K? 41,501. And I divide that by 26,253.67. I should be getting somewhere around 1.58. And this is in deaths per
mile.
100 million miles.
100 million miles.
And if we did deaths per mile, it would be like a really, really small fraction, right? So the reason why they go per 100 million mile is sort of like we can get a whole number out of this thing, right? I don't want to be comparing an annoying fraction. The other way is you could do deaths per mile, right? If you didn't want to convert this, if you wanted to do deaths per mile, and then multiply it by 100 million. That's another way to do this. 2, 6, 2, 5, 3, 6, 7, 1, 2, 3, 4, 5, 6. I get a really annoying small number. I have to multiply it by 100. 1, 2, 3, 4, 5, 6. 100 million will get me the same result. If I do deaths per mile and then multiply by 100 million miles, it works the same way. Just like we did that in the previous problem in some units like that. It was like, I think it was winnings per game, right? Or winnings for 100 games or something. How much are we making on one policy versus 1,000 policies? It is the same sort of concept that is coming up here. All right, so y'all got 2018 set up?
I've got a question on this solution though. I mean, so like it was 1.58. So would that mean that you round up or you round down in that death? Because I mean, you know, it's like you said, can't just have like 1.5 deaths or anything like that.
I would say it makes maybe a little bit of sense here not to round it or to just keep it like kind of like 1.58. This is descriptive. I know you can't like have a half a person die, but you're going to get 1.58 deaths per 100 million miles. If you do 200 million miles, it's going to be around like 3 deaths, right? So if you like start rounding things, it gets really off.
Okay, I see.
Yeah, if this was like giving us an even amount of people, or if it was asking for how many people would die, you might have to round this, right? If they're like, well, this person drove 100, there's 100 million miles on this, how many people would you expect to die? Probably 2 people, right? But yeah, I see what you're saying. But on these, I think it's okay to leave it a fractional amount because it's a death per this many miles. It's not actually just the unit deaths, right? There's this word per and then the miles that kind of changes it up just a little bit. And I think it's all right to leave fractions on things. It's a rate is what it is, I guess is what I'm
So the second one, okay, I know you're just doing the first one, Professor. So I'll wait till you do the second one, then I'm gonna ask.
I'll do it. Tell me how to do it.
Okay, so the 36560 divided by 32403.27 equals 1.12821189. So how? So it said 1.12.
So how'd you do your denominator?
I did it 36560 divided by 32403.
You moved the decimal, right? Is that what you're saying? Like right here?
Yeah, 0.27.
So you moved your decimal first thing. Okay. We're doing 36560 over 32403. 2403 was over 32K.
Yes.
36560, and we're dividing this by, yeah, put that on there, 0.27. 32. Ah. Can I type something in my calculator still? Let's see. 32,403.27. What are you getting, like 1.128? Something like that?
1.128, yes.
Yeah, that's it.
Okay. So, okay, so you don't round it? Okay. Oh, so you took
That's
the
pretty
third
close.
number. I stopped at the second number, like 1.12. So that's why I was asking you.
Yeah, you do one. Well, it should be 1.13, right? Should round up.
Yeah.
That's
Okay.
it. Good. If you do 1.13,
Okay.
1.12.
Okay.
So our deaths per 100 million miles doesn't look like it improved like a whole lot. Not quite as much as like the population, right? But it is a little bit safer. Especially when you're talking about billions of miles that we drive. Right? That thing would add up pretty quick. So you're talking about maybe saving half a person for every 100 million miles you drive. Or you'd be saving one person for every 200 million miles, right?
All right. All I gotta do is study this now, and I'll be good. Jesus.
All right.
Hey, Professor, can you give me an update on? Okay, so even though we did it and we're done, But can you just give me one update on this? What question is this again? Number 3, because I was just trying to figure it out. The what is the probability of getting a sum of 5? So we did the 6 squares, and that's the dice, right? The
Okay.
dice, one side dice, another side of dice.
This diagram.
Yeah,
Can I zoom out all the way? Can you see all this?
yeah.
This is my sum. How many different possibilities are there for the sum? And we're counting like the same. This is a different outcome from this is a different outcome, right? I'm counting all the different outcomes in here. How many different red numbers are in here?
So the number's increasing as you go down. That's what I didn't understand.
We're adding things. So this is adding 1 and 1 here, right? This is adding 2 and 1. We're adding these numbers. I'm adding the 2 black numbers where they cross. This is
Okay.
adding 1 and 1. This is adding 1 and 2.
Okay, I see now. Okay.
All right. This, if I pick somewhere in here, this is going to add 4 and 4, right? Each one of these numbers in here is the sum of the 2 numbers on the outside. So this is my first dice. I rolled a 5. My second dice, I rolled a 5. The sum of them would be 10. And the highest number that you can get when you roll 2 dice and add them is going to be what? 6
The
and
highest
6.
number I
Yeah,
can get is 12.
6 and 6 is going to give you 12, right? Is what this last one is telling me.
Yes.
1 and 1 is going to give me 2.
All right. So keep going.
Yeah, that's it.
Oh,
What
that's
else do you
it?
need to know? Yeah, go ahead and answer it. What else do you need to know? We want to know the probability of getting a 5. So how do you find that? How many different ways can you
There's
get a
4
5?
of them.
There are 4 different ways you can get a 5 out of how many different outcomes?
12?
Mm,
I mean 6. I'm sorry.
6 by 6.
12.
How many different things are in here?
Oh man.
I'm going 6 here by 6 here.
36.
There are 36 different outcomes in this thing. So there are how many again?
Right. 4 out of 36.
Oh, that's it. You just reduce the fraction.
Okay, I got it. All right. Thank you, Professor.
Yep. Yeah, that's it. We're like what, about 10 minutes ahead of schedule, maybe, right?
That means I'm getting good at what I'm doing.
Yeah, you get better. All right. So if y'all got questions, I will be around. I can go back over anything you want, anything y'all want to talk about. I'm gonna hit stop on the recording though, I think.